Plastic evaluation is our core expertise at Gradical. We help medical technology companies choose the right plastic for their application with the technical suitability, regulatory compliance, and improved sustainability. Learn more under www.gradical.ch/plastic-evaluation. Our guest today is Steve Maxson. He is an expert for medical extrusion and currently innovation and business developer at US-Extruders. He has over 20 years of experience in medical extrusion and hosts his own podcast, MedTech, where he covers all things medical extrusion. On the side, he also runs his own consulting business, Maxson Insight Services. Here's our discussion. Hi, Steve, and welcome to the podcast.
Hey, Lucas. Thanks for having me on.
Yeah, my pleasure. You're an expert for medical extrusion. What is extrusion and how does the process work?
So, yes, I'm involved in medical extrusion, but extrusion in general, just the basics on how it works. We're taking plastic pellets of a natural material or a compound that has additives blended into it, and we're feeding it into a hopper, and we're conveying it through the barrel and screw of an extruder, where we're generating friction and melting and metering, and we're going through a die head of some sort to, in my case, make small medical tubing. Mm-hmm. Or in many cases, it could be for a profile, for a window profile, window frame. It could be for a sheet or some kind of non-woven application. There's so many different extrusion applications, but in my case, we're making little tiny tubing like this that goes inside the body to deliver a medical device.
Mm-hmm. Okay, so it's everything that has like a two-dimensional cross-section, and on the third dimension is basically straight. Or are there different types of extrusion processes, and how would you differentiate them?
Oh, yes, there's many different extrusion processes. This is industrial and medical. Like I said, I focus on the medical arena, but there's millions of kilograms per hour of different plastics being processed in extrusion applications, from sheeting or films to fabrics for clothing, drinking pipe water, the water used to, the PEX piping to heat your underfloor flooring, so many different extrusion applications.
Okay. So, and extruded products in the medical industry, could you just name some examples?
Yeah. So in medical, we kind of split it up between inside the body and outside the body. So inside the body, otherwise known as minimally invasive, where we're delivering using catheters that are navigated through the tortuous anatomy to deliver devices, such as a stent to opening a lesion in a vein or an artery, so that blood can flow through the heart and through the peripheral, or maybe delivering a TAVR frame, a structural heart device within the coronary system, or peripherally below the knee, there might be a lesion, a blockage of an artery, and we're delivering a device. And that's kind of inside the body. And then outside the body, applications where we're delivering air, gases, fluids, drainage of fluids from the body from a procedure, simple packaging tubing where we protect these very sensitive devices, airway management. So, and that would be more, larger size tubing, like here's an airway management tube that's used, again, outside the body. There's some packaging tubing, right, to protect a guide wire or a stent, compared to the little tiny tubing like this that we're making for catheters, little tiny stuff, like this, flexible. So yeah, that's kind of in medical extrusion, inside the body, outside the body is kind of how we split it up.
Mm-hmm. And also delivering to the body. So for example, breathing circuits, anesthesia circuits, blood bags, and tubing that delivers basically an infusion of blood of some other sort, saline solution, stuff like that.
Yes.
And then the minimally invasive stuff. So what would you say these applications, these medical extrusion applications inside and outside the body, and maybe let's take the third one, like industrial applications where there's nothing medical. How do you see the different requirements for your extrusion, for the material, for example, or for also for the application? What are the differences in requirements? How would you differentiate that?
Yeah, that's a good question, Lucas. The medical extrusion market is more stringent than industrial as far as quality and biocompatibility, right? When we're talking about medical polymers, compounds, they have to be biocompatible. We're usually operating in a clean environment, whether it's a clean room or a controlled environment, to make sure there's no particulates, for instance, on the device that might go inside the body or, like you said, deliver drugs through infusion. So the medical extrusion isn't so much as high output rate, but more so high quality. Compared to an industrial application. Not that quality is not important by any means, but usually you're pushing output rate to get to the bottom line.
Okay. So it's more like the industrial applications that they have to have okay quality, but the throughput and cost is the center of interest there. And in medical, it's more of quality and consistency of output. Maybe also stuff like change control, supply security, stuff like that. And yeah, so tell us what kinds of plastics, what kinds of polymers are mostly used in medical extrusion and why?
Yeah. So kind of we'll start with the outside the body applications, like you said, infusion. That's typically, by and large, flexible PVC. Here's a dual lumen tube. I don't know if you can see it, with some stripe for drug delivery application. And that's a flexible vinyl, which is a huge, PVC is still, probably the largest from a kilogram or poundage annual. PVC is probably the highest volume of material used for infusion. And then for like some of the packaging tubing that I showed you, in polyethylene, polyolefins, polypropylene used for these kind of outside the body applications. And then inside the body applications, minimally invasive catheters are typically a composite of several materials and metals to give it the functionality for pushability, torqueability, flexibility. And so we're talking about typically a fluoropolymer like a PTFE on the inner lumen of the catheter, so that it can glide over a guide wire. Catheters go over a wire. So PTFE is the typical kind of the gold standard for the inner liner of catheters. And then typically we have what's called a multi-durometer section, where we have like a nylon 12 on the proximal end near the surgeon's end for pushability, more stiff material. And as we go down distally to the tip of a catheter, we reduce the durometer or stiffness, and we get really soft to the tip. So we might start with nylon 12 and different grades of or durometers of P-backs as we go down, and then possibly a polyurethane on the tip. And the same thing with balloons that are used for minimally invasive applications. Here's a balloon with some solution in it to give you an idea of a balloon for a TAVR or structural heart frame. And these are typically from the same materials because they need to be thermally bonded to the catheter shafts, and they need to be compatible. So they are typically nylon or P-backs or polyurethane as well.
Okay. So did I get this correctly? So you have like a material gradient from beginning of the tube to the end of the tube. How would you produce that continuously?
So you usually put it over a manufacturing aid or a mandrel, okay? A stainless steel, very precise rod with PTFE coating so that it could be removed. That's kind of the starting point because we want to add some kind of braiding material over it to give it the torque and the tensile and the flexibility as well. And in order to do that, you need to support the catheter or you'll just crush it. So there's typically a manufacturing aid called a mandrel, and then we're putting our PTFE over it, we're braiding over it, and then we're putting our multi as a gradient, like you mentioned, multi-durometer sections, and then we put it all into an oven, what's called a reflow oven, and we kind of fuse it all together, and then remove that mandrel. And this is all the fusing of all those different composite materials is fused together with a FEP or fluoropolymer heat shrink tubing, which is also a processing aid, which is removed as well as the mandrel. Take the mandrel out, remove that FEP heat shrink, and you have a reinforced composite catheter shaft.
Okay, so what you would do is you would extrude the different components and then like assemble it into a catheter and then basically thermally fuse it together. Braiding, you could maybe a little explain for the lay people what braiding is and what materials you would use for that?
Yeah, good question. So, like I said, the braid reinforcement gives it radial strength, the catheter radial strength. It also, depending on the braid pattern, gives the catheter, pushability or tensile strength, torque. If the surgeon rotates the catheter 180 degrees on the hub or the proximal end, we want to see a 1-to-1, 180 degree on the distal end. So the braid reinforcement gives you that functionality. And you can change the braid pattern along the length of the shaft. I was telling you how we can start with a stiff nylon on the proximal and go softer to the distal end to give it pushability on the proximal, but flexibility on the distal. We do the same thing with the braid pattern where we can modify the braid pattern to give you similar functionality. More modern catheters are seeing a replacement of that braid material, which is typically a stainless steel. And in MRI compatibility cases, you might use the polymer like a liquid crystal polymer or a PEEK for a braid reinforcement. But by and large, it's a metallic braid reinforcement. And those reinforcements for more modern catheters are being replaced with laser cut hypotubes, where you have a stainless steel or a nitinol thin wall, very precise tube that's laser processed, and you can laser process that functionality into the hypotube to give you that torque response and flexibility on the distal end.
Okay, so if you would do it with polymers, you would then basically also extrude PEEK to a very, very thin, basically filament and use that as braiding.
Correct.
Seems to be a very challenging task to process PEEK like that.
Yeah. It is unique. There's only a few people that do it.
Okay.
And there's people that might provide that material, but the strength, the tensile strength required for a reinforcement material, especially when you compare it to a metal, like the tensile modulus of a stainless steel is like way more higher than any plastic. So in order to kind of compete, you need to do some extra things to the plastic to increase the mechanical properties. So you typically draw it machine direction in line. So as you're drawing it, stretching it with heat, you align the molecules so that you have higher strength properties. So there's not a lot of people that do the drawed down PEEK or LCP filament for braid materials that really require the high mechanical properties.
Yeah, on top of the technical challenges, there is also the challenge of biocompatibility, change control, and all the quality issues. So I imagine those materials are quite a bit more expensive than stainless steel braiding.
Yes, actually, you're actually right. I have it took me a second to register, but I remember creating a bar graph of comparing the performance and the price of the polymeric braid materials compared to the metallic braid materials.
Okay, and it looks like that the performance of the metallic ones is way better and the price is way lower.
Yep. The reason you might need a polymeric braid material, certain applications, MRI, if you're using MRI, you want it to avoid the metals. So that's why you might use a polymer braid reinforcement for MRI compatibility.
Okay, good. Thank you for the insight. So now come the difficult questions. So you mentioned PVC and fluoropolymers. You're located in the US. That might be an advantage for the topic I'm following up on. It's material compliance. So number one, PVC, a very popular, historically very widely used material or additive to plasticized PVC is phthalates or phthalate plasticizers. They have properties of concern, so they are endocrine disruptors. They disrupt the hormone system. Sometimes you can accept that because of the benefit that the medical device brings you, but it's certainly being looked upon more critically, especially in the EU. They want to get rid of phthalates in the medical device. So that's the first one. And then the second one is fluoropolymers. In the US, I don't think that you actually label fluoropolymers as a PFAS, parent poorly fluorinated alkyl substances. And in the EU, they do, which I think is a mistake, because fluoropolymers are basically essential for these kinds of applications that you have there. You might elaborate on what you think about the topic, and secondly, if there is any alternative, or that you think that there is an alternative for certain applications. Credical is the plastic expert in medical technology and supports you in the areas of sustainable plastics and material compliance. Our course, Sustainable Plastics and Medical Technology, will bring your development team up to date with the latest developments in sustainable plastics. In addition, we offer the course Regulatory Aspects of Plastic Selection at the CATS and the SCATZ, which provides guidance through the maze of regulations when selecting materials. More under www.credical.ch.
Yeah, the PVC, let's start with that one. That's been going on for many years, and it's not PVC, it is the phthalates, right? And so a long time ago, we got rid of the certain, I think DEHP or some of the problematic phthalates and additives have been removed. And I know a gentleman from Foster. Foster's a compounder of medical materials, and there's a gentleman that I know there has been in the industry for 30 years, and he said he's been involved with many potential replacements of PVC through his 30-year career. Not one of them have actually been implemented because the material is so friendly to process. It's flexible, it's clear, it's bondable. There's not a real great replacement material for PVC, and then you're talking maybe 2x or whatever more in cost. So PVC is a great material to process, to work with for medical device applications. Been around a long time. It's just, like you said, the phthalates that you need to worry about, and that's been taken care of. Fluoropolymers and PFAS, you mentioned a couple times Europeans, the EU. I tell you what, I talked to a friend of mine in China, one of the major medical processors for minimally invasive devices, and I asked him about it. He said, "We don't even think about it." And so there's such a disparity in, I guess, how we look at these things, and there's really is no alternative, for instance, to PTFE. There's no material that has the properties, the lowest coefficient of friction of any material is PTFE. It has great biocompatibility. They call it, you could call it a forever chemical, but if we're using it to coat a stent or to cover a stent that's going to be a long-term implant, you want it to be very durable and last forever, to have those properties, right? So I know there's a lot of this is something that's been talked about a lot over the last couple of years, and hopefully there'll be cooler heads will prevail, and there'll be exceptions for these fluoropolymers used in medical and aerospace applications.
Mm. I mean, I always say this: if someone can tell me what the difference between persistence and chemical resistance is, then I'll be happy to hear that. Because I mean, the point is something that lasts forever. Yeah, is very chemically resistant. That is actually what you want if you have an implant. You don't want it to erode or to be chemically attacked by the body somehow. And on the other hand, I mean, this is one property of fluoropolymers. Number one, it's very chemically resistant. Number two, it's very temperature resistant. And number three, it has a very low coefficient of friction. And if you need all three, you have no alternative. If you need one of these properties, you might find something else. I think for minimally invasive devices, you're kind of stuck with them. And I mean, they have some derogations for like 12 years, but you can probably elaborate on how much time would you need if you have to develop a polymer. I mean, if you develop a polymer and you're fast and you can industrialize it, you have like 3 to 5 years. So now 7 years for developing a minimally invasive device and go through approval and all the clinical studies. Is that realistic?
You know, I had someone on my podcast, a brilliant lady formerly from Edwards Life Sciences, a polymer science person that's done a lot of research and implemented different polymeric solutions for medical device applications, implantables. And she said it takes 10 years just for of clinicals and testing, just for the surgeons to even, or doctors to even consider it an alternative material for an implantable. So think about how long it would take. Now that's an implantable. We're class 3 device, I guess. We're talking about class 2 devices, kind of in and out, less than 30 days. But yeah, I think that 5 to 7 year time frame is probably accurate. And there are people, a lot of people right now evaluating alternatives to PTFE, for instance, as an intercatheter liner, just to be, have a backup plan in case there is, kind of further regulatory challenges. And so some of these compounds of these materials, nylon PBACs with additives, low friction, like hydrophilic additives blended into the base polymer to reduce the friction, are one of the solutions. High density polyethylene, quote, the poor man's FEP or PTFE is also considered, but there's challenges with all these different solutions.
I mean, and in the end, if it gets banned completely, I mean, you're back to like having open surgery, and then that's a step back. Because I mean, minimally invasive surgery, there's a reason why you do that, because it's minimally invasive and the stay in the hospital is considerably shorter, and that will drive up costs, of course, and it will probably also worsen outcomes. And that's a thing. So let's see if I mean, I still have hopes that the EU shows some common sense. I mean, I'm not a European citizen. I am I'm a Swiss guy, so we do our own thing. But I mean, you have to know that what it is decided in the EU, Switzerland will probably take over a lot of it due to so-called bilateral agreements that we have. And I mean, it's also like, if you look at on the other side of that, I mean, this is the chemical regulation stuff, and then you have also the medical device regulation. So the EU MDR that put a lot of requirements on medical device companies that are making like niche devices that really make them basically unaffordable. So number one, you have like price caps what certain procedures can cost. And then on the other side, you have a certain amount of approval cost that you have to calculate using the MDR because you have these requirements. And then if you have a certain number of cases per year, so if you have like 1,000 cases or 100 cases a year, there's no way you can earn money with that device. So what they will do is they discontinue it, or they make a big publicity stunt out of it and say, we will produce this anyways, and we will lose money doing it because little children will die otherwise. And I mean, Switzerland is thinking about just accepting FDA approval, US FDA approval, and saying, hey, if it's good enough for the US, it's probably going to be good enough for us. And we're just going to have like the EU MDR and the FDA. And my kids will have devices that EU kids will not have. And I think this is quite a challenge. I mean, of course, devices and in general products should be safe to use. But on the other hand, I mean, you have a certain benefit with the use of certain substances, and these benefits can sometimes justify the risks that you have. I mean, maybe some insights from your side or some opinions on that regulation topic. Do you enjoy the podcast? Then subscribe and rate it on your platform, and join the discussion on LinkedIn. Your feedback and comments help us improve the podcast and bring relevant topics to you. Let's form a better world with plastics.
Yeah, no, I think you nailed it about MDR. I think, some medical device OEMs are just taking products off the market, right? Because it's not worth it. Except in those cases, like you said, where you're, saving a baby's life, for instance. But I was talking to a regulatory person that I know the other day that handles all the quality requirements that's a consultant that works with the medical device contract manufacturers, and said that the MDR and some of these regulatory, the model is for the OEMs to pass on work to the contract manufacturers, whether it's building a catheter or extruding a tube, or more and more of those services capabilities are being passed on to the contract manufacturers. And beyond kind of processing, molding, extruding, and things like that, the regulatory burden is also being passed on to the contract manufacturers, and it's created a situation where you're increasing your overhead to deal with some of the new regulatory requirements from MDR and environmental and social. It's just things that people aren't accustomed to handling in MedTech. Quality used to be you just get ISO 13485 and off you go. You got some staff to handle that, but there's more staff, more overhead because of the increased burden of that regulatory, and a lot of it has to do with MDR.
Yeah, I think I can agree on that. I think if this analogy is correct, I think so. The contract manufacturers is like middle management for the whole industry. So on one side you have the material manufacturers that usually have a very good market placement. If you do specialties like medical plastics or medical grade plastics, implantables or specialties, you have a very good position. So it's not that everybody can do these materials. Mm-hmm. So they have a very good market position. And then the other side, you have the OEMs that basically own the product, usually also are big device manufacturers. And then the contract manufacturer in the middle is like bullied from both sides. And that then makes it a very difficult position to be in. And they even lack like design so you lack design authority, so you cannot basically change the design of your device, material of your device. You have all these requirements, and then this just leads to the situation that you have to tell your OEM, hey, do I have to charge more because of all these things? And then they basically they basically try to force you to accept just the overhead and produce at the same price. So it's not an easy position to be in. Maybe you could elaborate on some anecdotes from your side.
Yeah, just to comment on what you said about the pricing for a contract manufacturer working with an OEM. If they're, sometimes there's our supply agreements that kind of lock pricing in over a period of time based on volume, but usually you don't have a lot of opportunity to raise prices except for materials. It's like you can't raise prices, say, hey, our labor went up, our labor rates went up, and we need to increase prices. That's difficult for a commercial person to pass on to an OEM. But if your material costs go up, then typically you can raise prices. So, we went through a period during COVID where, and beyond, where the prices were just going up on a lot of these materials, and the supply was a challenge. And fortunately, a lot of the contract manufacturers were able to pass on those price increases to their customers.
So the only thing that you have left is just keep the prices high from those increases and not let them go down again.
Right.
But I mean, the OEMs, they're also fast in negotiating prices downwards and upwards. They try to avoid that. Yeah. So another topic that I am very involved in is sustainable plastics. Also sustainable plastics and medical device. I mean, of course, you're working a lot of in the body class 3 devices. This is not usually the first topic that you're talking there. But I mean, you have a lot of consumables that are outside the body, maybe circuits, maybe blood bags, and these are consumables that are used a lot and end up usually in waste. So the environmental impact there is the thing. So how do you see the potential in the extrusion space for sustainable plastics? How do you see that?
Yeah, that's a tough one in medical, like you mentioned, certainly in minimally invasive, but outside the body, same thing, biocompatibility, need good, properties and such. So I just haven't seen, I probably never have seen the introduction of recycled content in a medical application personally, where you might take some scrap, for instance, and reprocess it and introduce it in and back into the extrusion process, like many industrial applications. We were talking about PVC earlier, and construction, or rigid PVC used for window frames and such. You can recycle up to 100% of rigid PVC and extrude it and have very similar mechanical properties, maybe a minor reduction in properties that's probably not noticeable. So materials like that, many applications, you can reintroduce scrap into the process. But for medical applications, I have never seen it.
Yeah. So, I mean, there are different kinds of sustainable plastics. So I have an example of a PCR mechanical recycling material used in, it's not an extrusion process. It's injection molded. It's a tip for an otoscope. So basically a device with which a physician looks into your ear, and that's the tip that basically just covers the device. So very similar to like an optical fever thermometer. And few seconds of body contact, and they do it from they make it from a recycled fridges. So it's probably polystyrol, recycled polystyrol. So it is possible. Also, from a regulatory perspective, it's possible. Of course, you have a lot of quality and risk management challenges, and it also depends on basically the risk class of your device. Very low risk, you can probably do it. For implants, you will never do it. There are very, very, very few polymer suppliers that actually support doing implantable devices over 30 days. So that is the first thing. And then secondly, sustainable plastics. Many people think of sustainable plastics. Yeah, of course, it has to be recycled. I mean, it can also be chemical recycled, which then has very similar to exactly the same properties, which you would then introduce over something called the mass balance principle. And then you have also bio-based alternatives. So especially for the polyolefins, you have a lot of alternatives to use as feedstock. So basically, if you can do biogas or if you can chemical recycled oil or something like that, you can use that as a feedstock as you would like petrochemicals. And then you have the exact same properties. Biocompatibility is the same. And then there are special cases where you can have like physical content. For example, you mentioned PA12. I'm not sure if it's the PA11 or 10, but you can have certain oils in nature that have the chemical properties that you can derive feedstock for polyamides from them that are basically bio-based. Mm-hmm. And the advantage is, of course, that the bio-based materials take up CO2 from the atmosphere and reduce your carbon footprint significantly. So there are alternatives, but of course, I think the sustainability trend is catching on also in medical, but as always, medical takes a little more time. Or, I mean, maybe it's also a little different in the US and the EU, because in the EU, I see certainly the trend that they have more the focus of sustainability. I have heard from a customer who developed a consumable together with me. They visit 12 customers and show them the consumable. Hey, this is now from bio-based plastics. Do you want this or not? Guess how many of the OEMs said, yeah, we need this? 12 out of 12.
Really?
12 out of 12.
Wow.
Yeah. Oh. This is really a trend. And we will see. They will do a US tour, and we will see how the trends differ there. So yeah. I'll keep you posted on that.
Definitely.
So make a guess. I think they're visiting like 10 customers.
Okay.
Make a guess, and then we'll see if that's if that is accurate.
I'll go 5.
Okay, 5 out of 10. Okay.
Yeah.
That's probably a good guess. So you had a stellar career in medical extrusion. Would you like to tell us a bit about this?
Yeah. I grew up in a town called Pawcatuck, Connecticut, and there's a company located there, been around for probably over 100 years, called Davis Standard. And this company manufactures extruders and extrusion systems. And my father worked there for 47 years. And so, he was a hard worker, and he always worked on Saturday mornings, went into the office, and he sometimes would bring me in, and I'd get to see machines and extruders, and kind of liked it. And I went to school as a mechanical engineer and ended up working at the same company that my father did for about 5 years as a mechanical designer. And there was a gentleman there that used to sell medical extrusion systems, and I was just so intrigued by him and what he was doing. And I just kind of over time wanted to work for him. And I pleaded and begged and worked at night so I can kind of learn about medical extrusion from him. And I was hired on to help him as a project manager, put line layout drawings together, work with the engineering group to put these medical extrusion systems together, and got accustomed to some of the company names that he sold to. And I just wanted to be like him. His name was Charlie Sparacino. And there was some time after where a group of people from Davis Standard, Bill Kramer, the technical director, Ed Stewart, may rest in peace, the director of process technology, left to start their own company called American Kuna. And I joined them shortly after and started this medical division. And we became kind of the leaders in North America in medical extrusion systems. That company was owned, majority ownership was Peter Kuna of Kuna GmbH out of Germany. And it came time for him to want to sell the business, his portion of the business. And we became acquired by Graham Engineering, a large machinery manufacturer of blow molding equipment. Didn't really know much about medical, but stayed on with them for a little bit over time. And now I'm with US-Extruders, a great company selling medical extruders and extrusion systems. So I've been involved in this medical extrusion space for over 20 years. I also sold extrusions. I was the VP of sales for a company called Spectrum Plastics Group, one of the largest medical extrusion operations in North America, probably the largest for medical. And so I got a lot of experience selling extrusions and catheter design services as well.
Okay. So you went from extrusion, and then as soon as you could, you went into medical, and then basically stayed there for your whole career. So you were always on the extruder part, so the machinery. And did it never occur to you that you have to switch sides and go to basically a contract manufacturer or something like that?
Yeah. I reached a point where, I always wanted to get more into the full assembly, the full catheter development, assembly and design, and then just kind of sticking to the extrusion. Every catheter starts with a good extrusion, though, so remember that. But yeah, so I wanted to get a little bit more involvement in the full contract design and manufacturing. So I really love that space. And my podcast, I interview and have host many people from contract manufacturing side.
Okay, cool. So tell us a bit about your podcast and how that came about.
Yeah, I used to do these events they're called Spotlight, where I rent a room or a hotel space in a cluster where there's a large amount of contract manufacturers and MedTech companies, and have an event where I bring in different people and we talk about different topics. But that model where you bring people in and somebody sits in front of a screen and gives a PowerPoint presentation gets a little old over time. You want to have a dialogue. So I thought, let's have a podcast where we can have an open discussion like you and I are having, Lucas. And I started it. We're on our second season, over 30 episodes, again, talking mainly to thought leaders in contract manufacture and medical device OEMs.
Okay, cool. So if you want to check it out, the podcast, I'll put a link in the description.
Thank you.
And then we will come to the last question. What advice would you want to give to our listeners in regards to medical extrusion?
Lucas, we need more talent in medical processing, whether it be extrusion, molding, reflow, whatever the process. We need more young people that want to get involved. There's an institution in the Boston area called UMass Lowell, and that's traditionally the plastics engineering program at UMass Lowell has brought out so many great individuals that are involved in the space. And they used to have 60 people, students enrolled annually in that plastics engineering program. And now with all the negative publicity about plastics, they're lucky to have 10 people, students enrolled in that plastics engineering program. So there's just a negative attitude towards plastics, and we need to change that. It's really exciting. It's a great field to be in. Medical plastics and medical processing. You're working in a clean environment, developing therapies to save people's lives. We need more young talent in this space, and we need to do something about that collectively.
I couldn't agree more. I mean, it's exactly. This was an analysis that I did when I founded my own business. So number one is, what can you do good? So I'm good in plastic selection and regulations, material compliance, stuff like that. So how many people can do that? Probably not as many as you think. Mm-hmm. So, and how many are needed? Probably a lot more than people think. So my bet is that there are not enough medical plastic expert, and I think I will win the bet.
Yeah.
So any last words?
No, I really appreciate the opportunity to come on and talk about some of these topics, interesting and important topics, Lucas.
Okay, good. So for everybody listening, this was Steve Maxson from US-Extruders, and until the next time. Still looking for more in regards to plastics and medical technology? Visit our website www.gradical.ch and inform yourself on the services of Gradical. You can also check out our market report on medical grade plastics on www.medicalgradeplastics.de. Or you attend a training regarding material compliance at CATS or at SKZ. And of course, don't forget to rate and subscribe our podcast wherever you get your podcast. Let's form a better world with plastics.